We're going to take a look at some practice problems. And these practice problems are on page 116 and 117 of your text. And they are numbers 21 through 24. So let's take a look at number 21. Boron has two isotopes, boron 10 and boron 11, which I'm abbreviating like this. Which is more abundant given that the atomic mass of boron is 10.81? Well, if we would look at boron on the periodic table, on your periodic table and specifically, boron has atomic number 5. Its atomic mass is 10.81. That's what we would see when we looked up boron. And here are the two isotopes. So these are designating boron's mass numbers. So all we need to do is compare the mass numbers of these two isotopes of boron to the atomic mass of boron, and which one is closer? Well, 10.81 is closer to 11. So that would tell us that boron 11 is the more abundant isotope. Okay, remember that the average atomic mass is a weighted average, so it's going to be weighted towards the more abundant isotope. Its value is going to be closer to that more abundant isotope. Number 22 is a similar question. We have three isotopes of silicon: silicon 28, silicon 29, and silicon 30. If we take a look at silicon, silicon is atomic number 14, and its average mass, as given, is 28.086 atomic mass units. Okay, so what we want to do here is describe the relative abundance of these three isotopes. So just as in the problem above, we're comparing the mass numbers of the isotopes to the atomic mass. Which one is closer? Well, silicon 28 has a mass number that is closest to the average atomic mass of silicon. So silicon 28 would be number 1 in abundance. Okay. After that would come silicon 29, and then silicon 30. All right, because 28 is closest to 28.06, and then 29 and then 30 is furthest away. And the other way you can think about it is like if you had a number line, and if this is where 28 is, that's where 29 is, that's where 30 is on the number line. 28.086 ends up right about here. And you can see it's closest to 28, and then 29 is a little further away, 30th is farthest away. So the order of abundance is listed right here. Let's take a look at number 24. I'm sorry, number 23. I'm getting ahead of myself. So number 23 now is discussing two isotopes of copper. The element copper has naturally occurring isotopes with mass numbers 63 and 65. So we have copper 63 and copper 65. The relative abundance and atomic masses are going to be given here. Okay, so the relative abundance for copper 63, okay, the abundance of copper 63 is 69.2%, and the mass is given as 62.93 AMUs. 62.93 AMUs. It's my old eyes. I have trouble reading those little letters. For copper 65, the abundance is 30.8%, and the mass is 64.93. Okay, so we're checking our abundances. 69.2 plus 30.8 does equal or add up to 100. Our relative abundances must add up to 100. So what we want to do is calculate the average atomic mass of copper. So here we go. The first thing we do is take the abundance and turn it into a decimal. So 69.2% as a decimal is 0.692. So we have 69.2% of this isotope that has this mass of 62.93. So we're going to multiply that percentage by 62.93. And then we're going to add it to the next abundance, 30.8%. We're turning that into a decimal, which now is 0.308. And so we have 30.8% of the isotope that has a mass of 64.93. So we take 0.308 or 30.8% times 64.93. So what this equation literally is saying, if we could take this mathematical equation and turn it into English, it would say 69.2% of 62.93 plus 30.8% of 64.93. Okay, so we have this percentage, 69.2% of an isotope with this mass plus 30.8% of an isotope with this mass is going to equal what mass? And it's 63.6 AMUs. Okay, and you can compare that to the average atomic mass of copper on your periodic table. Now, some periodic tables, when you look it up, it might be listed at 63.5 instead of 63.6. That might be a rounding issue. You will see some differences of about 1/10 or 100th on these atomic mass units, on these average atomic masses, going from periodic table to periodic table. Number 24, we want to calculate the atomic mass of bromine. The two isotopes of bromine have atomic masses and relative abundances of 78.92 AMUs. So the first mass of bromine, here's my bromine right there, the first mass is 78.92 AMUs. And the abundance is 50.69%. And the other isotope of bromine has a mass of 80.92 AMUs. And its abundance is 49.31%. So when we add the abundances together, 50.69 plus 49.31 does equal 100%. So we want to double check that. Okay. We're doing the same thing that we did in number 23. So we'll take the abundance of the first isotope of bromine, 50.69%. We're turning it into a decimal. That's 0.5069. And we'll multiply it by its corresponding mass, 78.92. And then we add that to the next abundance, 49.31%, expressed as a decimal, which is 0.4931, multiplied by its respective mass, which is 80.92. So what our equation says is 50.69% of the isotope of a mass of 78.92 added to 49.31% of 80.92 AMUs is going to equal 79.91 atomic mass units as our average atomic mass of bromine. Okay, notice here that my answer has 4 significant figures, and that's because all of the values in my original equation had 4 significant figures. So my atomic mass is expressed out to 4 sig figs. If we go up to number 23, the atomic mass of copper was expressed just to 3 sig figs, and that's simply because we had some numbers in the original equation that had 3 sig figs, so we had to follow those rules for rounding. Okay, so just as a summary, the average atomic mass is a weighted average of the masses of the isotopes. So we need to know not only the masses of the isotopes, but we need to know their percent abundance.